So today we'll look at using limits to help us describe continuity. Continuity, if you look at a graph, continuity is easy to see. It's just wherever there's a break in the graph, where if you follow the graph with your pen, you have to jump to go to the next point. But there's some details we need to describe in order to describe that analytically instead of just looking at the graph. So reviewing, we have talked about limits, and so the limit at 1 is 1 because the y values are going to the same value of 1. So we can say the limit as x goes to 1 is 1, but the limit at 2 does not exist because the y values from the left are going to 2 and from the right they're going to 3. So the limit does not exist. Today we're going to add these concepts, and that is one-sided limits. We're going to go to 2 from the right. So let's approach x equals 2 from the right, and we'll look for the y value that it's approaching. It's approaching 3, and now we can talk about the behavior of a graph even when it's not continuous. Let's go to 2 from the left, follow the graph from the left, and the y value is approaching 2. And we can follow the graph, go to 3 from the left. So here, even at an endpoint, we can talk about the limit, and we're going to approach 3 from the left, following the y values, and the y value is 2. The limit, the one-sided limit at 3 is 2. Alright, the y values don't matter. We're going to try to come up with a rule for continuity. These can be approximate y values just relative to the other points. Alright, and we're going to look at x equals a, and we're going to talk about its continuity, and we'll talk about at x equals a, is the graph continuous? Can we trace the graph without lifting the pen? No, we have to trace, stop, jump, put the point, and then come back down. So it's not continuous at a, and that's called a jump discontinuity. Does the function exist at a? Is there a point at a? Yes, the function exists. Does the limit exist at a? The limit exists if the y value that is approached from both sides is the same. The function approaches the same y value from both sides, so the limit exists. But is the function value equal to the value of the limit? And that's no. All right. Is the function continuous at B? Can we trace the graph without lifting the pin? So, yes, the function is continuous. Does the function exist? At B, is there a point? Yes, the function exists. Does the limit exist? Is the graph approaching the same y value from both sides? Yes, the limit exists. And is the function value equal to the value of the limit? Yes. All right, you try C. Pause the video. So at C, is the function continuous at C? Tracing the graph, we have to jump. So it's not continuous, and that's a jump discontinuity. All right, and we have, does the function exist? At C, is there a point? Yes, the function exists. Does the limit exist? Is the function approaching the same y value from both sides? No, this is up here, this is down there. The limit does not exist, and that means that they can't be equal. Okay, pause the video and try D. What's happening at D? If we trace the graph from the left, it's going to negative infinity, and from the right, going to positive infinity. We cannot trace it without lifting the pin, so that is not continuous, and that's called an infinite discontinuity. Does the function exist? No, there's no point at D. The function does not exist. Does the limit exist? No, because the function is going to in different directions, and that means that we can't say that they're equal. So let's check E. Pause the video and try E. At E, can we trace the graph without lifting the pen? We have to stop and then start again, so we have to lift the pen. It's not continuous, and that's called a removable discontinuity. We'll see why it's called removable. Does the function exist at E? Is there a y value? No, there's no y value, so the function does not exist. Does the limit exist? The y value that is approached from both sides, the function approaches the same y value from both sides, so the limit exists, but we can't say that they're equal because there's no function value. So it turns out that these three things, these three statements, are required, and we can see that here. The only time that it was continuous was when we had a function value, the limit existed, and they were the same. Anytime we have one of these that is a no, then it was not continuous. So that leads to continuity at a point is the limit as x goes to a of f of x is equal to f of a. And this is just stating the same thing that we looked at in those three characteristics when we wanted to see if the function, the limit, and are they equal. So here we're looking at the function, the limit, and are they equal. This statement has three things that we have to check every time. We can also have continuity at an endpoint. So if we have a graph on an interval, is it continuous at the endpoint? And we can say it's continuous at x equals a if the limit as x goes to a from the right is equal to f of a. It's continuous at x equals b if the limit as x goes to b from the left is equal to f of b. It's just the same statement as this, but we have to use one-sided limits because there's nothing on the beyond the endpoints. All right, and then these require a little practice because it's just discuss the continuity of f, and we have to find where the discontinuities are. And if we have a graph, that's easy to do. We'll say f is continuous everywhere, but f of x is not continuous at and we want to say that, well, here let's look at 0. We know it's not continuous at 0 because, and then we have to look at what part of this requirement is not met. So does the limit exist at 0? Yes, the limit exists because the function is approaching the same y value. The limit exists. Does the function exist? No, the function doesn't exist. So we say because f of 0 does not exist. But we want to recognize this as a removable discontinuity. All right, so you describe the other discontinuity and what's the reason for that discontinuity. Pause the video. So we follow the graph. We see that we have to lift the pen to trace the rest of the graph. So there's a discontinuity at x equals a because, and then we look back up here, we can say that does the limit exist? No, the limit does not exist. Does the function exist? No, there's no function value. And we can just say either one of those. We can say f of a does not exist. That's enough to say that it's not continuous. We can also say that the limit of f of x as x goes to a does not exist. But we can describe it thoroughly by saying that it's an infinite discontinuity, and that's removable discontinuity. All right. So let's just combine. Let's talk about a one-sided limit. Let's see what's happening as x goes to -2 from the right. If we just substitute a -2, we're going to get a vertical asymptote. To check, we'd have to check on either side of -2 with a table. We can also look at a graph. And we know at -2 that it's going like this. Let's see what happens over here later. So at -2 from the right, follow the graph from the right, and the limit is -infinity. If we didn't have the graph, we would just substitute, and we can do it like this. That's going to be 4/0. We know that this creates a vertical asymptote because the numerator is not 0. But to see what's happening to the right of -2, we could substitute -1.9 and see what happens with -1.9. We know that the limit is -infinity because of the graph or because we checked a point to the right. Discuss the continuity. Well, we know there's a discontinuity at -2, so we would say let's just make sure we throw a reason in there. And because f of -2 does not exist. It's a discontinuity because f of -2 does not exist, but this doesn't imply this. The infinite discontinuity we have to verify graphically or numerically. But let's not stop there, because we have another issue. At -2, the denominator is 0. And at +2, we have 0/0. So if we looked at the limit of the function as x goes to 2, we get 0/0. When it's 0/0, that's called indeterminate. In indeterminate form, we're going to have a removable discontinuity. And when we look at just the function, look what happens. We have -1/x plus 2. So this graph is the same as this graph, except that except when x equals 2. If I put a 2 here, I get -1/4, and that's going to be the open circle on the graph, the missing point. All right, so we can say that the limit as x goes to 2 equals the limit as x goes to 2 equals -1/4. And here the work is up here, and that work would be done down here, but I'm just using this expression here. So we say removable discontinuity at x equals 2, and we can say f of 2 does not exist is a reason for a discontinuity. All right. Pause the video and try this one. You should use a table or a graph to analyze this. All right, if we graph that, we can graph it on the calculator. Remember that on the calculator, you press Math, Num, and Abs, and that'll give you absolute value. And the graph is, we have a problem, division by 0 at 2, and it turns out the graph goes like this. What's the limit at 2 from the right? Let's go to 2 from the right, and the y value that is approached is 1. The limit as x goes to 2 from the right is 1. Discuss the continuity. We can look at the graph. We know it's a jump discontinuity, and then we just have to state the correct reason for the discontinuity. So it's discontinuous at x equals 2 because, and we are looking back at this. We want to know, does the limit exist, does the function exist, and are they equal? So looking at the graph, does the limit exist? No, the limit does not exist. Does the function exist? No. And we can just say either one. The limit as x goes to 2 of f of x does not exist, and that's enough to say that it's not continuous. This can be graphed on the calculator. It's pretty easy to graph by hand too. I'll just give you the graph and then you can answer the questions. Okay, pause the video and answer the questions. All right, the limit at 1 from the right. Follow the graph from the right, and we're approaching a y value of 0. Approach 1 from the left, going to 1 from the left, and the y value is 1. And then continuity. We want to check, does the function exist? Yes. Does the limit exist? No, because from the right we're approaching 0. From the left, we're approaching 1. Because these are different, we would say that the limit at 1 does not exist. The limit at 1 has to be the same from both sides. So we would say it's discontinuous at x equals 1 because the limit at 1 does not exist. Okay, and we'll stop there.